Okay, is the screen visible to you?
Yes, sir.
Yes, sir.
Okay, so let us recall what we discussed yesterday. If function f from x to y is bijective, right? If function is bijective, then what happens? There exists a function g from y to x such that g composite f is identity on x and f composite g is identity function on y, right? So then g is called as, what is g? Function g is called as,
Bijective.
function g is called as inverse
Inverse.
of f. Okay, now similar kind of thing we do with real numbers. So if you have a is equal to 2, what is inverse of 2? Multiplicative inverse of 2. What is a inverse? Is 1 by 2, correct? And what is a product? A into a inverse. That means 2 into 1 is 1. What is a 1? 1 is identity, correct? And what is identity function? We are talking about identity function and here identity of real number. So the philosophy is similar, right? What do we mean by inverse? And what is the role of multiplication played here in case of functions? What is a multiplication in case of functions?
Composite.
Composition, very good. Therefore, so now you can think as a set of all functions and you define the composition, correct? Then there is a similar kind of things happening. There is a operation, composition, and you can talk, have a identity function also. So many things are there, inverse of function, correct? Okay, so also we saw that one more thing, if f is from x to y, so and g is from y to x, such that g composite f is identity on x and f composite g is identity on y, then what happens? Then what happens? F and g are both bijective, correct? F and g are both bijective functions and g is f inverse. G is actually inverse of f, right? So now from this, can you observe that if f is from x to y, g is from y to x, g is f inverse, then what is g inverse? What is g inverse?
F.
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 Inverse is f, right? That means g inverse means what? G is basically what is f inverse, and we are looking at inverse of it, so it is f, right? So can you prove this? That is a proposition. So what is a proposition? So if f from x to y is a bijection and f inverse from y to x is an inverse, of f, then what is f inverse of inverse is f. And this is very easy to see, right? We understand. We can easily say that inverse of inverse is f. So it is exactly same that inverse of 2 is 1 by 2. And what is inverse of 1 by 2? Again 2. Right? Inverse of 1 by 2 is 2. So the similar thing, inverse of inverse is itself. Right? And what is the proof of this? So what is the proof of it? So since f from x to y is a bijection, f is invertible. F is invertible. Therefore, f therefore f inverse from y to x exists, and f inverse composite f of x is equal to x for all x in x, correct? And f composite f inverse of y is equal to y for all y belongs to y, that we know, right? So let g is equal to f inverse. Suppose I am giving different name to f inverse, which is g. Therefore, g composite f of x is equal to x for all x in x, and f composite g of y is equal to y for all y in y. Okay, so is it clear what I am writing? What I am saying is clear?
Yes, sir.
And therefore, so now this situation is symmetric in f and g. No problem which is the first and which is second. The composition of both is identity, and therefore what we can say, therefore what, f is inverse of g, right? F is inverse of g, that means f is nothing but g inverse. F is nothing but g inverse means f is actually g inverse. But what is g inverse? G itself is a f inverse and its inverse, and therefore f is equal to f inverse of inverse. Correct? Okay. Now, if function is bijective, we know that inverse function exists. Now my question is, if f is from x to y, g is from y to z, right? Then suppose these functions are bijective. So this is set x, this is set y, this is set z, f, g. Suppose, so g composite f is bijective function, right? If g composite f is a bijective function, can you find inverse of g composite f, right? If g composite f,
Yes.
g composite f is from x to z, right? Is bijective, then we can find its inverse because this function is bijective, its inverse exists. Then what is its inverse? Because certainly we can talk about inverse because it is a bijective function. And so the question we can raise, what is the inverse of composite function? Do you understand? So f and g are functions, and then g composite f is bijective. Then we are interested in now what is g composite f inverse. This is our interest now. Right? So question is clear. Yes. Is the question clear?
Yes, sir.
Right. Okay, so let us think about this. So suppose f from x to y, g from y to z are bijective functions. Then, which we have already proved, G composite F is from, what is the domain of G composite F?
X.
X to
X.
Z. Is
Y.
it bijective? Is it bijective?
Yes. Yes, sir.
Right. So because we already proved that if both of the functions are 1, 1 and onto, then composition is also 1, 1 and onto. That we have already proved, right? So it's bijective and G composite F inverse. So now certainly we can talk about inverse because it is bijective. So what it is, right, is nothing but F inverse composite G inverse. Right. So let me draw the figure so that you can understand it. Key what I mean want to say. This is my set X. This is my set Y. This is my set Z, and so this is my function F. This is my function G, and now both are bijective. So this is G comp. Now I am interested in the reverse way. I am interested in what? G composite F inverse, right? Because G composite F inverse is from Z to X. Naturally, from this figure, what it should be? What is the way from Z to X? From this figure, you can observe what is the way to go from Z to X. What is the reverse way for G composite F? Naturally, what should happen?
First from Z to Y, then Y to X.
Right, this is a natural way. That means suppose you want to you go from Kolhapur to Mumbai, then you first go to Pune and then Mumbai. And what is the reverse way naturally? You go from Mumbai to Pune and then Pune to Kolhapur. So this is a natural way, right? We'll go from here to here and here to here. So what is this from Z to Y? This is G inverse and this is F inverse. And therefore, what is a process? Process is apply G inverse and then F inverse. So therefore, in this proposition, which function is applied first? In inverse case, G inverse
Genius.
and then F inverse. So this is a process, this is a mechanism that you can observe. Okay, so we want to prove this. How to prove this? What is the strategy? What is given? F from x to y and g from y to x are biject functions. But now from this figure we see that we should first apply g inverse then f inverse. But what is the guarantee that g inverse and f inverse exist?
F and G are both are bijective.
Very good. So f and g are bijective. So no doubt f inverse g inverse exists, right? Therefore, f inverse from y to x and g inverse from z to y exist. Z to y exists, right? So the inverse functions exist. Now, what is our claim? So first claim is कि G composite F from x to y is biject.
So the function G is from Y to Z now.
Oh, here y to z, right? Then G inverse is from Z to Y. Correct. So our first claim is G composite F is bijective, right? So which is already proved in the previous discussions, right? What is the second claim? What is second claim? Correct? Yes. Whatever you are, whatever we are discussing, everything is clear.
Yes, sir.
Okay. Now note one thing. So let me. What is the second claim? G composite F inverse is a function now. And what is the right hand side? Is again composition of two functions. It is a function. We want to say that these two functions are equal. These two functions are equal. Means what? So note this. Suppose you note this. What I should use notation here. Suppose phi and psi are two functions from A to B. Their domain is same. Then phi is equal to psi. These two functions are equal if and only if. What is the definition of equality of two functions? When we say that two functions are identically equal, we have discussed this already.
If they are subset of each other.
Which phi and psi are functions. Okay, you are confused with phi. So let me use some different notations. So what notation I should use here? Okay, let me use notation f and g, no problem. When we say that two functions are equal, functions are equal means what?
Sir, fx is equal to gx for all x belonging to the domain.
Very good. So fx is equal to gx for all x in domain. That means if their action on every element of domain is same, then ultimately functions are same. Right? If their action on every element of domain is same, then functions are same. For example, so if I define f from R to R, f of x is equal to x square. And I define another function g from R to R by g of x is equal to x square if x is not equal to 0 and 1 if x is equal to 0. Are these two functions equal? Right. What is the first function f? Graph. And what is the second function? G. G is also x square except at x is equal to 0. At x is equal to 0, value of function is 1. Are these two functions same?
No.
Is it true that f of x is equal to gx for all x in R? Is
No,
it?
sir.
No, because for x is equal to 0, fx is not same as gx. Therefore, the condition that they agree at every element of domain fails. Therefore, these two are not same function even because they differ at one point, right? So two functions are identically equal if they agree. They do not differ at any point. That means they agree at every point of the domain. That is what is the meaning of two functions are same. And what is our second claim? Our second claim is कि left hand side is a G composite F inverse as a function and right hand side is F inverse composite G composite as a function, and we want to say that these two are same. Right. So now our claim is clear. What we wish to prove. right? So therefore we claim that what we claim now, what we claim, G composite F inverse is from what to what? What is the domain of G composite F inverse? What is the domain of G composite F inverse?
Z from
Z.
Z.
Right? And therefore, what is our claim? Ki these two functions are equal on which domain? Right? G composite F inverse is
Z.
right. So what is our claim? Our claim is ki G composite F inverse of Z is same as what? F inverse composite G inverse of Z for every Z in Z. If this is true, then can you believe that ki G composite F inverse is F inverse composite G inverse?
Yes, sir.
Right? So we claim that ki this thing is true. Okay, let us try to prove this. So once your aim is clear, our goal is clear, then with confidence we can try to prove it. If your goal is not clear, then there is no confidence, right? So if your aim, what is our exact claim, if it is clear, then certainly we can understand what should be the strategy. So what should be strategies? How to initiate the process? How to initiate the process? Our goal is clear. Ki for every element in Z, these two things agree, then we can say that ki these two functions are equal. So this is our claim. So how to initiate the process? How to initiate? See this line. Read this line carefully. What is our aim?
G composite F inverse of Z is equals to G of F inverse Z.
See, whatever you are saying is not wrong but not appropriate. Suppose I give you a box containing fruits and I ask you prove that ki every box in the every fruit in the box is sweet. Prove it. What you will do? Right? Suppose I gave you a box containing fruits and I ask you prove that every fruit in the box is sweet. What you will do? You will first open the box and you will choose a fruit and you will test it. Then you will take second fruit, another fruit, you will taste it, keep it away, right? You will take another fruit, taste it, take it away, and you will find that every fruit is sweet. Is it clear? This is a process, natural process. Yes.
Yes, sir.
Same thing we are going to do here. What we will do? Take a element from Z, open the box, and take a Z. So how to start the process?
We will first find taking an element of Z, finding the G composite F, then finding its inverse.
And then prove that the result is same, right? So
Yes.
open the box and choose arbitrary fruit and check that it is a sweet. That means you just close your eyes and choose any element from Z. And if it's for that element Z the equality holds, then we believe that for every element it is true without any bias, right? So first, so naturally, see, you should think always with logically what we are doing. So first of all, choose element, arbitrary element from Z and apply these two functions on Z and you check whether the result is same, right? Be any element. choose any element from Z, right, and then apply, right, then what? Then what? Since G is onto, there exists Y in Y such that G of Y is equal to Z, correct? That means G inverse of Z is equal to Y. Correct? So we have selected Z from Z. There is a Y here. So and we are looking at particular Z, and we found some Y here which corresponds to this Z. Right? Further what you can do? Y is in Y
F of
and F
x
is
equals to y.
so Y is in Y and F is bisective, means onto, there is X in X. Further, since F is bijective, so there exists X in X such that Fx is equal to Y. That means X is equal to F inverse of Y. X is equal to F inverse of Y. Right? So we started with Z, we found Y, and from Y we found X. Right? Therefore, what is G inverse? What is F inverse composite G inverse of Z? We started with this Z. What is F inverse Z G inverse of Z? What is it? F inverse of
Y.
Z G inverse of Z, which is F inverse of, but G inverse of Z is Y. Right? These are very specific elements, right? Because we have selected a particular element Z. For that we found Y, and for that Y we found some X. So these are very specific elements when we select a specific element Z. Right? But F inverse of Y is X. That means F inverse composite G inverse of Z is X. Then next, what is G composite F inverse of Z? If we apply now this function on Z, what happens? Next, okay. Let me not write this directly. What is G composite F of this X? What is G composite F of this X? This particular X. What is it? G of
Z.
Fx. That means G of Y, and G of Y is Z. Now, can I say that G composite F inverse of Z is actually X? Am I right?
Yes, sir.
Yes.
And therefore, if we apply G composite F inverse on Z, and if we apply F inverse composite G inverse on Z, the result is same X. Right? Am I right? Is X, which is same as F inverse composite G inverse applied on Z. Is it clear? Action is same. Yes, do you agree?
Yes.
And therefore, what is the condition? Since Z belongs to Z was chosen arbitrary, right? So we did not select Z just very biased. We just close eyes and selected Z, and for that Z this is going to happen. Therefore, can I say that G composite F inverse of Z is equal to F inverse composite G inverse of Z for every Z in Z. Is it going to happen? Yes.
Yes.
And therefore, can I say that these two functions are actually same? Right, so these two functions are same, and therefore G composite F inverse is F. Now the question I would like to ask, is it true that G composite F inverse is G inverse composite F inverse? Is it true? Does it make sense?
No.
It doesn't make sense because the domain of G composite F, right, F G, and this is G inverse, this is F inverse. So domain of G composite F inverse is Z, but domain of G inverse composite F inverse is what?
X.
No, domain of G inverse composite F inverse. First we apply F inverse. So what is the domain?
Y.
So this is from Y to X. But G inverse is not defined on X. So this doesn't make sense. This is not possible because these two are not equal. Right? Therefore, you have to worry about, you have to take care of order. G composite F inverse is F inverse composite G inverse, the reverse. But in case of real numbers, right? So if A is equal to 2 and B is equal to 3, what is 2 into 3? Okay, what is 2 inverse? What is A inverse? That is 2
1
inverse.
by 2.
1 by 2. What is B inverse? 1 by 3. That is
1
3
by 3.
inverse. But what is AB inverse? 2 into 3 inverse, right?
1 by 6.
1 by 6, which is 1 by 2 into 1 by 3. 1 by 2 into 1 by 3. Actually, what is it?
A inverse to B inverse.
Right. So it is 1 by 2 into 1 by 3, which is 1 by 2 into 1 by 3, which is A inverse into B inverse. But in case of real numbers, it is also same as B inverse into A inverse because in case of real numbers, AB is same as BA, commutativity of multiplication. Due to this property, in case of real numbers, there is no difference. But in case of functions, this is not going to happen. Right? So, but do you find any such situation where AB inverse is same as B inverse into A inverse, but not same as A inverse into B inverse? Where is such situation? Where is this possible?
In matrices.
Matrix.
In matrices, very good. So if A is A and B are 2 by 2 matrices, right? A and B are 2 by 2 or whatever, 3 by 3 matrices. Then AB inverse is B inverse A inverse, and it is not same as A inverse into B inverse. So in case of matrices, this hold. Right? Therefore, this makes sense ki when we find inverse of some composition, then in general the order reverses. Correct? Okay, so let X is equal to set of all 2 by 2 matrices with real entries. right? So this set is denoted by M2R. M2R means set of all 2 by 2 matrices with real entries. Right, for example, if I take A is equal to 1, 2, 5, 7. So this is a member of set X, correct? Can I say that this A is a member of set X?
Yes.
Or X is also denoted by M2R, 2 by 2 matrices with real entries. Now, question I would like to ask, can you define a function f from X to R? Can you define a function from set of matrices to real numbers? Can you think about such function? Do you understand? Can you define? Can you relate matrix with real number? Right? Do you understand? Can you relate matrix with the real number? That means can you define a function? Okay. From this matrix, can you obtain some real number? Can you do some process on this matrix so that you will get some numbers, real numbers?
Find its determinant.
Very good. Determinant. So define a map f from X to R by f of A is equal to determinant of A. Is it a real number? Determinant is a real number now?
Yes.
Right. That is f of A, B, C, D. Right. So this is a member of set X 2 by 2 matrix. Then what is this? AD minus BC, and it is clearly a real number. So is it a function now? Can we apply this function on every matrix, every element in set X? Yes. So can you apply this? Is it a function? Is it a function or not? Is it a function? Can you find determinant of every matrix?
Yes.
So can you apply
Yeah.
this on every element of set X?
Yes.
Yes, no doubt. You take any matrix, 2 by 2 matrix, apply determinant, it is a real number, so it is a function, right? But I would like to ask, is F11? Is F11?
No.
No. Why? Because you can find two matrices A, for example, 1, 0, 1 by 2, and I will take another matrix 1 by 2, 0, 0, 1. These are two matrices, different matrices, but what is f of A? What is f of A?
1/2.
1 by 2. And what is f of B?
1/2.
Right? So and A is not equal to B. Two elements are in the domain are unequal, but their images are equal. So not 1, 1. This function cannot be 1, 1. Is it clear? Next question I would like to ask, is f on 2? Is f on 2? That is for any A belongs to R, does there exist matrix A in X such that f of A is equal to A? What do you think? What is it? 1 1?
Yes.
Yes, for example, if A is equal to 5, then what is a matrix A such that f of A is equal to 5, that is determinant of A is equal to 5. Can you find such matrix? And it is very simple. What is determinant of A?
5.
5, right? And therefore f of A is determinant of A is 5. So we can actually produce the matrix. So in general, if I take A is equal to A0, 0, 1, then what is f of A?
A.
A,
A.
right? Is it possible for every real number? For every A belongs to R, there exists A in X such that f of X is equal to A, f of A is equal to small a. Correct? Therefore, f is onto. Now, is f bijective?
Yes.
No, sir.
No.
No, because it is not 1 1. So this function cannot be bijective function. Now, can you define any other function from same set to real numbers? Right? Suppose you have some matrix, some element of X. What another process you can do so that you will get a real number? Is there any other process? Determinant is a one process. What is another process?
A in
Hmm? Trace. What is a trace of matrix? Sum of diagonal elements. Right? Sum of diagonal elements. Sum of diagonal elements. So if in this case, what is trace of A? A plus D. Diagonal elements means elements on this main diagonal. So sum of diagonal elements A plus D. So is it a real number? Trace of a matrix, is it a real number?
Yes.
So define G from X to R by G of A is equal to trace of A. Is it a function now? Then you can think about, is G11, is G onto, is G bisect. Correct. So question is clear. You just think about it like previous problem. Now I want to define. Can you define a function f from x to x? That means function f from x to x. That means 2 by 2 matrices to 2 by 2 matrices. What is this? M to R, and this is also M to R. What function you can define from matrices to matrices? If you apply function F, you should get same matrix. Suppose A is equal to A, B, C, D. So what process you can do on this matrix so that again you will get a matrix?
Transpose of A.
Right, transpose. So what is a transpose? A transpose is what? Convert rows into columns and columns into rows. So AC, BD. So this is A transpose. And where is it now? Again, it is a matrix in same set. Right? So therefore, what function we can define? So define f of A is equal to A transpose. Right? Again, you can think about key is f11. Is it a function? Right? This question might be difficult, but you can think about. Is f biject? So you should understand that there are functions from only real numbers or natural numbers or integers are not sufficient. You can think about some general sets, functions from matrices to matrices. What is another process? Transpose is the one process. There are many processes you can apply on matrix so that you will get again a matrix. Right? Is there any other process?
Multiplication of matrix.
No, but we are applying f on a matrix. Then you should get a matrix. So where is the multiplication? That is again correct, multiplication, but what way? Right? Okay, so what you are saying is not wrong, but do you know what we mean to say? Which multiplication? We are applying function on A and you should get matrix. Where multiplication? We are going to multiply with whom? With which matrix? Okay. Choose some matrix P. Choose some matrix P and then define. So this matrix is fixed. Okay, what I am going to do, suppose I have a function A is equal to 2 and I define a function from R to R. F of x is equal to 2x. Is it a function from R to R? F of x is equal to 2x. Is it a function? Yes. F of x is equal
Yes, sir.
yes, it is a function because I am multiplying by some constant, right? Or I can say that f of x is equal to ax, whatever a you select. So this is a function, and basically here every real number is a 1 by 1 matrix, and 2 itself is a 1 by 1 matrix. Now I have selected a particular matrix P, and so what function I can define? Define f from x to x. What is f of a? Can I multiply? So every time I will multiply by P with A. Is it a 2 by 2 matrix? P is 2 by 2 matrix. A is 2 by 2 matrix. And what is a product? Is a 2 by 2 matrix.
2 by 2.
Right. So in that way we can, but we have to fix some matrix and then multiply every matrix by that matrix. That is a function now. Correct? Then you can think about is F11, is F12, right? Is F biject. So these questions are not very easy to answer, But you should think about it. There are such functions also. Okay, now let us go to the next situation. Let C is equal to, there are many functions you can define. The way is, just think about what process you can do on matrices and what is the result. In that way you can define many functions, right? You can take inverse, but inverse is not defined on set of matrices, because what happens if I take matrix A is equal to 1 2 2 4, then A inverse does not exist, right? Therefore inverse is not a proper function on this set. But you can think about this function by on a subset of X, correct? What is set C? Set of all complex numbers. Set of all complex numbers. What is actually this set? X plus IY. X and Y are real numbers and I square is equal to -1. Right, so this is my set. So okay, what function you can define on set of complex numbers? Can you define a function from complex number to complex number? That means if we apply complex function on complex number, you should get a complex number. Yes. What is the trivial example? F of z is equal to z, identity function, right? That means f of 2 plus 3i is 2 plus 3i. So it is a function from complex to complex, correct? Yes. What is another function? Different function, different from identity. What process you can do on complex number so that again you will get a complex number? What process?
Addition of complex numbers.
Where is addition? Which numbers we are going to add? I am going to apply function f on z, where addition will come. That is possible, but in different sense.
Conjugate.
Conjugate x minus I1, right? So we can apply. So define f from C to C by f of z is equal to z conjugate, right? F of z is equal to z conjugate. Now question I would like to ask is f11 is f11 what is f of 2? And what is f of 3 plus 5i? Is it 1 1? Okay, what is f of 2?
2.
Because 2 is actually 2 plus 0i. And what is its conjugate? 2 minus 0 is again 2. So 2. But what is f of 3 plus 5i? 3 minus
3
minus 5.
5i. So is f11?
No.
No.
Why no? Why no? Suppose f of a plus, suppose z1 is equal to a plus bi and z2 is equal to c plus di, and suppose their images are same. Suppose f of z1 is equal to f of z2. That means f of a plus bi is equal to f of c plus di. But by definition, what is it? A minus bi is equal to c minus di. Now we are saying that these two complex numbers are equal, a minus bi. So when two complex numbers are equal, if real parts are equal and imaginary parts are equal. What does it mean? A is equal to C and B is equal to D. What does it mean? Z1 is equal to Z2. Yes. And geometrically what happens? If you look at complex number 1 plus I, and if I apply function, what I will get? 1 minus I, which is here, which is a mirror image. Mirror image. And therefore no two elements will go to the same element. So clearly it is a 1 1. Right? Second question I would like to ask is f on 2. What is your answer? Is it on 2? Is it on 2? For example, if you look at w is equal to c plus di in codomain, pre-image z, so that f of z is equal to w. What is its pre-image? Can you produce pre-image so that f of z is equal to w? Yes. What is pre-image of 2 plus 3i? 2 minus 3i. Because what is f of z? What is the image of this 2 minus 3i?
2 plus
2 plus 3i.
Which is w. That means for any w, can you produce pre-image? In general, if w is equal to c plus di, what is the pre-image?
C minus di.
C minus
C minus di. It is very easy to see because therefore for any w is equal to c plus di in C, there exists z is equal to c minus di in C such that f of z is equal to w. So it is onto, right? Therefore f is onto, and therefore is f bijection.
Yes.
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 Now can you find a function f from C to R? Complex numbers to real numbers. You think about it. Yes. Is it clear? You think about, can you find a function from complex numbers to real numbers? How do you read it? There are many such functions, so you think about it.
Yes.
You can take modulus, you can take real part, you can take imaginary parts. There are many functions, so you just think about it and which of them are 1 1 on 2. So many things are possible. Okay, so we'll stop here, and we have discussed many things about functions.